Hello everybody, this is Dr. Vev, and I would like to take this opportunity to thank Shu Wing Tam, who made a comment below my original video 87 pointing out a small error I had made there. And when I analyzed the error, I realized I had made two errors, not just one, and those two canceled out to give me the correct residue. So if you've not done it, please take a look at that video. At the 6-minute mark, we analyzed the residue of the function f of z, which is z to the power half over 1 plus z squared, which means I need to set the denominator equal to 0. So if I do z squared plus 1 equal to 0, this is going to give me z squared equals minus 1, which can be written as e to the I pi plus 2 pi ki. And when I take the square root, I get z equals e to the I pi by 2 plus pi ki, where k can be either 0 or 1. If k equals 0, then I get the first value, which is e to the I pi by 2. I'll call that I pi by, which I'll call z1. And the second value, when k equals 1, gives me z2, which is e to the 3 I pi by 2, or 3 pi by 2. This turns out to be plus I, and that turns out to be minus I. But it's very important for us to realize that plus I is written as e to the I pi by 2, and minus I is written as e to the I 3 pi by 2, and not as e to the minus I pi by 2, which is the error I made in the previous video. Now, if I want to find the residue of this function f, it's going to be 2 pi, well, the Cauchy theorem says it's 2 pi I times the integral value is 2 pi I times the sum of the residues of the function f. So I'm going to get 2 pi I times the limit. It's going to be two limits. So limit as z goes to z1. I'm going to write this denominator as z plus I and z minus I. So if z goes to z1, which is plus I, I'm left with z to the half over z plus I, and then limit as z goes to z2, z to the half over z minus I. So let's carry this out with some degree of care. That's 2 pi I times, well, z goes to z1 means z goes to I. So I'm going to write this as I to the half over I plus I, which is 2I. And that I'm going to write as z goes to z2 means it's going to minus I. So it's minus I to the half over negative 2I. So now, without making any mistakes, I to the half is going to be the square root of that. So that's e to the I pi by 4 divided by 2I. And there's a minus sign that goes here, as Shu Wing correctly pointed out. Minus I, however, is written as e to the 3I pi by 2, and that, if I take the square root, becomes e to the I 3 pi by 4 over 2I. Now, the 2 cancels out, the I cancels out, so I'm just left with pi times e to the I pi by 4, which is cosine pi by 4 plus I sine pi by 4 and then e to the I 3 pi by 4, which is cosine 3 pi by 4 plus I sine 3 pi by 4. We're almost done now. That's pi times cosine pi by 4 is 1 over root 2. That's 1 over root 2. Cosine 3 pi by 4, because 3 pi by 4 is in the second quadrant, it's 135 degrees, is negative 1 over root 2. And sine 3 pi by 4, since sine is positive in the second quadrant, is still that. So what happens is that these imaginary terms cancel out, and that gives me pi times 2 over root 2, because it's 1 over root 2 plus 1 over root 2. That's minus of plus, and that's root 2 pi. The answer I got was correct, but I made two mistakes in getting it. The first mistake was writing negative I not as e to the I 3 pi by 2, but rather as e to the, I wrote this as e to the minus I pi by 2, which it is, but you're not supposed to do it. So that's a mistake number one. And mistake number two was a silly algebraic mistake. I ignored the negative sign here. But making those two mistakes together gave me the correct answer. So this video corrects those two mistakes.